mark because it's easier to calculate. You realize this curl of vector field f was 0, right? You calculate that. That means now is a gradient vector field. This f is gradient vector field of something, right? So I'm claiming that f is 1/3 x cubed plus 1/3 y cubed minus 1/2 z squared. If you do the partial with respect to x, you get that one, right? Partial with respect to y, you get that one. Partial with respect to z, you get that one exactly. So that is gradient vector field. So you can use fundamental theorem of line integral because of that. But they wanted to use the Stokes theorem, and that's fine too. So you see the connection between this thing? Yeah. So here is lined up like this. FB minus FA. Closed curve, that's a 0, right? Started at A and ending at the same thing. Then you enter the line integral like that. dr, right? What is the third item? Stokes theorem. What are you putting down there? Surface S. So curl of gradient vector field going inside and the normal vector in dA, right? What is the curl of gradient? It was a 0. So that's a 0. So this example is using this connection right there. Right hand side is 0. Right? Think makes sense? Okay. Alright, how about this one? That is involved actually, I believe this is non-zero quantity, nothing like that. So let's try this one. This is your exercise, but we have to kind of think about what's in this thing. Exercise number 3. Let's write this one down and understand what the problem is saying. C is a curve. It consists of 3 straight lines joining 2, 0, 0, 0, 1, 0, 0, 0, 3. And we're going to evaluate the line integral of this vector field around these 3 segments by using Stokes theorem. If this were triangle in down there in xy plane, what are you going to do? What theorem are you using? Green's theorem, that's right. If it is line integral of different segments like parallelogram all happening in xy plane, then we use Green's theorem, right? Because that's more convenient parameterization. Okay, so let's sketch this one and understand what that is at least. YZ. So 2, 0, 0, that's about here. Is that right? 0, 1, 0 is about here. And 0, 0, so it's all the way up there. So that's the triangle there. Talking about this one to that, and to that. So that's the direction. That's the direction. That's the direction. If you have to compute this one directly, you have to parameterize the surface, right? Correct? And how would you parameterize this surface? Do you think this Monge parameterization is kind of available? If so, you have to write this plane as a z equals something, f of xy, right? Do you think it's possible to write this thing? So what kind of equation is this? Not quadric surface, right? But it's a plane equation. It's the plane, right? So do you think you can come up with a plane equation? You need normal vector, doing the cross product of one of these two, and use one of those points, and you can get that point out of it, right? Make sense? So whatever that situation, but the best scenario is that if this one has a curl 0, then we don't have to do any of this thing, right? So I guess that's the first thing you have to compute. Go ahead and check if this curl of this one is a 0 or not, right? If it's non-zero, then it is necessary to go ahead and compute all these things, right? But I think the curl is non-zero, so I'm going to do that here for you. Let's calculate the curl. We need that anyway for surface integral. xy, yz, and xc. What's the curl? So This part's 0, that's part's negative y. Did I have this right? We do that part 0, and that part's z. So this part's 0, and that part's x. So do your curl. Check with me. So agree with my curl calculation? So for that one, there's no y in there. There's negative y. So if you do that one first, it's a 0. If you do that one, it's negative z. For the third one, there's no x in there. So there's x in the plus x. All right, you get this, curl? So curl is non-zero. So by Stokes' theorem, that we have this integral around this line integral is equal to this surface there, right? So which way do you think it's oriented if it must have the same orientation? If you put your right-hand rule around this thing, is a normal vector coming toward us going opposite way? If you do the cross part, the right-hand rule of this orientation of this curve there. It's coming toward us, right? So would that be alright if I put the normal vector there and it's sticking out like that? That's the direction of a normal vector of this oriented surface. When you do the Stokes theorem, you must have the same orientation. This one is going around like this, right? If you put your right hand pointing with the four fingers going around like this, and your right hand is pointing this way, right? So this S must have an orientation to make sense out of this, and this is the orientation we have. Yes? The third one here? Yes, this one is a 0, right? Thank you. This one is 0. This one is 0, and that one is x in the negative x. Thank you for the correction. Okay? And then this one, it's going to be negative y. Now I'm going to do that curl of phi. That with n and dA. Okay? Since curl is not 0, and we're just going to calculate this one directly. And then we have to parameterize S. That's the main test cue. Okay? So there's the 3 vectors. What was the idea of parameterizing this thing? You come up with this plane equation, right? Plane equation, and SNT is not going to be 0 to 1 and 0 to 1 because SNT is x and y. So here's a little triangular region. Okay? But first you have to come up with compute the equation of the plane. Then we're going to have this equation, that's the main key. Then think about S varying from where to where and T varying from where to where. That's a secondary. This is the main part. So go ahead and compute the equation of line, and we're going to check our answers together. Not equation of this plane here. Yeah, it's still number 3. Stokes' theorem requires any plane, any surfaces that closes this one, right? So it could be a complicated surface, but the simplest thing is that if it's a plane, it's still going to work. So S is the plane we chose. But if you choose something else, like blown up version, still having this boundary, still the integral is the same, surface integral. So how is a plane equation? Do you agree that the vector AB is -2 if you subtract this vector, this position from that, -2, 0, that's 1, and 0, that's vector AB. Vector AC, which I calculate this one, is -2, 0, and 3. So if you do the cross product, you will get the vector there. Maybe I did this this orientation, do you think is correct? Maybe I did orientation get the wrong. So if you do that, oh, I think it's right. If you do the right hand rule, this is the first vector, I did this one. This is the second vector. If you do the right hand rule, thumb is still pointing out this way. So this is a correct orientation that coincides with this one. Okay, so think about, here's one vector, AB. Here's vector AC, right? And this is the first vector and second vector. That's how you point in the right hand rule, and then pointing this way. So that is pointing out this vector is actually in that direction we wanted. So this is the correct one. If you choose this vector, cross product this one and that one, that would be this vector and that one, that would be incorrect. But if you do this one and that one, first and that one, yes. A to B and B to C? Yeah, that would be A to B here and B to C there. So that's correct too. Because if you do B to C, if you parallel transport, B to C is over here, right? But if you transport it here, that's the same, yeah, the same thing. Yeah. But did you get the different number than? Right. So this is right. So if you transport and join the initial point together, then apply the rule. Any question? All right. So that's the function. Right. From there we have parameterization available. So x equals s, right? Y equals t. That's the amount of parameterization. What is z? 1/2 -3s -6t plus 6, right? You see where s and t is coming from? This is x coordinate and y coordinate, correct? So in this plane, the triangular, the shape in there, do you see how the x and y is varying? What is the idea to figure out x and how is x and y are varying? Is a projection of this plane onto xy plane. That's all you have to do, right? Project this triangular plane onto xy plane. But do you see that it is this triangular region? Everything falls onto that. Therefore, that triangular region is called R. And this is our parameter space, so we're switching to ST integral over that region R. Okay. So that's our parameterization for capital S, the surface. What we are asked to compute here is a line integral. Line integral around that oriented surface C of a phi dotted with dr is by Stokes' theorem. What is it? The surface we chose that has this boundary S and the curl of the vector field we started with, which was this xy, yz, xc, but we calculated here dotted with RT, right? With the dA. Sorry, this is supposed to be n. Thank you. Then we enter parameterization, right? This is a parameterization, free rotation. So what do we write down there? R, that's what I denoted. And understand this R is not square or rectangle. It is a triangular region. Then what is our curl? Negative y, negative z, and negative x. Negative y, negative z, and negative x. Dotted with our RSRT. This is a modular parameterization, right? Here's modular parameterization. So what was the formula? Negative Fs, right? What is negative Fs here? Positive 3 over 2, correct? How about negative Ft? That's positive 3, 6 over 2, right? And what was the last component of a modular parameterization? 1 if you partial, 1. So this is ds dt. All right? So let's enter complete ds dt version. This is R, that triangular region. What is negative y there? Y here is a t, right? Simply t. And negative 3, what is a z? Z is this version here, just 1/2 times negative 3s, negative 6t plus 6. Negative x here is a negative, x is s, and that's ds dt. Fair enough? Three came from that, and z came from here. So z is a 1/2. This is z, right? 1/2 negative 3s, negative 6t plus 6, and 3 came from here. Why did this one get positive? Yeah. I apologize. Watching out. This one becomes then remain negative, right? No, that's positive there because of this negative z, and that was positive. That was negative 2, right? Oh, that was negative, positive. Right. It was a negative fs. It was negative fs. It was negative ft, right? That was the modular parameterization. So negative is multiplied there. So that becomes positive. It's negative multiplied there. That becomes positive as well. So positive 3 were correct. Right? Yeah, because that's how the modular parameterization work. Negative fs, negative ft, 1, that's RSRT for modular parameterization. So negative is multiplied after you partial to the partials. So both positive. So when you multiply, we pick up a negative. When we multiply these two, we pick up negative again. Right? Yes, so that will correct. Make sense? Yes. Okay, yeah. At the beginning, you have to have the C and S in the correct same orientation. For the orientation of a C is going around like this, right? Well, so you know this is a correct orientation. So pair the two of the vectors here. If I pair this vector and that direction of the vector, then this is the first vector cross product the second vector. That's how you do the right hand rule for the cross product works. This is the first vector pointing to second vector like this, and then your thumb is pointing out. Yeah. Okay, immediately you got it. Right. So this one has to be broken down. S going from where to where? S is going from 0 to 2, right? So S is going from 0 to 2. T is not going from 0 to 1, right? T is going from 0 to the line equation, whatever the line is. I think it's 1 minus half t. I think that's 1 minus 1/2 s. And the same thing, ds dt. Remember how the double integral break down when the region is not rectangular region? I believe the line down there is y equals 1 minus half of x. That's the line there. So I use that 1 minus half of x now to do this integral. Right? This is the double integral with a non-rectangular region. Then we're going back to session 3. So that's the answer. Sorry about the delay. And there were